Hey, let's finish what we were doing earlier here. So we had that, let's just briefly go over what it is that we did so far. So we got the number X of game systems sold in a week is related to the price P in dollars of each system. When the price was 220, that means 20 game systems were sold in a week. When the systems went on sale the following week, so they were worth less, they sold 40 of them. That's not a big surprise, right? They cost less, they sold more. All right, so write a linear function that models the situation. So we got done with this part. What we did was we said, okay, well, I know that a linear function's got to look like that. So if I've got a linear function, any linear function ever has to look like this. So what we did was we said, well, I got to find this m. So I said 2 points on our graph have to be these, right? Because our ordered pairs looked like this. We had X was the weekly sales, right? X is the weekly sales. And then the price or the cost here was our y value. So that's how we came up with these two ordered pairs. So we have two ordered pairs. We use those to find the slope of our function, right? We had change in y was this number minus this number. Change in x was this number minus this number. So that simplifies to -3/2. And we put 3/2 negative right there. So we had to find that b value. We can use either one of these ordered pairs. Writing this in function notation, if I've got an ordered pair, there's my x value. That is the f of x value, right? So I can say f of 20 has to be 220. So same thing here, right? If I put in the x value 40, I'm going to get the y value 190, and that's how we would model this with our function notation. So pick either one of those you want. It doesn't really matter. If you put 20 through the function, we got to get 220. So that's what we did here, right? We put 20 through the function, and well, we got 220. We just took this nice equation that now we know that this has to be true, and we said, hey, I know that that's true, and I can just solve for b. And we did. We found that b was 250. So we wrote our nice function there, a linear function. All right, now we're up to speed. So the question we had here is, what is the applied domain? Well, let's draw a picture of this, because I think drawing a picture of this would make, this was part A, right? I'll just write, A was right there. So part B, what is the applied domain? Let's draw a picture. If we were going to draw a picture of this function, we can plot points maybe. If I put x equals 0 in there, I'm going to get 250. So 250 is up here, and I'd put a dot there. So if we're looking to draw a picture of a line, we need 2 points on the line. We've got 1 point on the line there. And this is the point 0, 250. And we would also want maybe we could use this other point, that other coordinate, the X-intercept. Let's draw that one. So X-intercept, we could find the Y-intercept just because of the form of the line, right? B, this has to be the Y-intercept. So that's how we found that. X-intercept, we're going to solve f of x equals 0. And we can maybe do that right here. So if I've got 0 equal f of x, yikes, that's pretty tiny. But we'll finish this up real quick. So if I subtract 250, okay, and now I'm regretting making this so small, but we can probably get over it. So we wanted to say what x would be 250 times 2/3, whatever that is. So that'd be 500 over 3, whatever that is. So we're pretty well scrunched up there, but we found the x-intercept, and it's over here, right? 500 over 3, comma 0. And, that's probably good enough. So if we're asking what the applied domain is, the linear function that we just wrote looks like that. if we're over here with our X values, that would mean that the number of sales would have to be negative, right? Remember that X values are a number of sales. So here in the negative region with our X values, that would be a negative number of sales. So that would mean that we're giving away units, right? We're just giving them away. Instead of selling them, we're just, hey, here you go. And then, all right, the other end of this is if we are past 500 over 3, then that means that our cost is going to be negative. And in a real life application setting, if our cost is negative, if our revenue is negative that we're getting, we're losing money. So anything past 500 over 3, we're going to be losing money on these units. So we ought to, not lose money on these units. So we wouldn't want to have any X value beyond this one. So when we're saying what's the applied domain, we would probably say that it would be 0 to 500 over 3. Because anywhere left or equal to 0, we're going to be giving away systems. And anywhere to the right of 500 over 3, that's again our X-Intercept, anywhere to the right of this, we're going to be giving people money to take them. And that's, not very good business sense. I don't know what our backgrounds are necessarily, but certainly I think we can agree that a business giving away a product isn't a good idea. And a business giving you money to take a product also is a pretty bad idea. So this is, wow, that's super, super busy. So let me get a new sheet here and we can do these other problems. Let me write down what the function was that we had. All right, so we've got, there's our function that we decided modeled this problem, right? And we can do the rest of these. If the retailer wants to sell 150 items next week, what should the price be? Okay, well, our ordered pairs look like this, right? So our X values are number of sales. And if the retailer wants to sell 150 systems, we're doing part C, use X equal 150 because this is the number of sales, right? So we would do F of 150, and that's equal to negative 3 halves times 150 plus 250. And, multiply this out, and that's what that is, right? And we can do that. Either do this by hand or do this in your head. We can, we could totally do that. Maybe we'll leave that as an exercise for you to do because that ought to be routine, right? We can multiply these things together. All right, so now what? D, we want to do D. What would the weekly sales be if the price were set to 150 per system? So now this is kind of inside out, right? Instead of giving you sales, we're giving you the price or the cost. So we would want to say F of X is equal to 150 here. So we can solve this for X, right? Because I know what my function is. And I would just want that to be equal to 150. So we can do that, right? We would subtract 250 from both sides, and we would get negative 100 equals negative 3 halves X. And then X would be equal to 100 times 2/3. So that's 200 over 3. So that's how many units we would sell. Supposedly, if we dropped the, or excuse me, that's the, yeah, that should be our weekly sales if we drop the system's price down to 150 bucks. All right. So now that we've done this, I feel kind of cheesy for not doing this because we could, right? This would be what, 150 divided by 2, that's 75 times 3 would be 225. So 25 25 bucks. So if they wanted to sell 150 systems, they'd have to price them at 25 bucks, which is pretty low, right? All right, so we are done with that problem, parts A through D. How wonderful. And let's talk about what's on the back of this sheet as well. So definition 2.3, let f be a function defined on some interval. The average rate of change of f over the interval ab is defined as what? So average rate of change. We already talked about what slope means. Slope is the rate of change of our function, right? It's the change in y divided by the change in x. And so far, all of the problems that we have had have been lines, and the rate of change has been constant. But there's no saying that we can't compute this for a curve. Like if I had some weird looking curve like this, who knows? And I wanted to know what is the average rate of change between this A value here and this B value here. Well, couldn't we just find the slope of the line that contains those 2 points? Because that's going to be your average rate of change, right? So if we connect these 2 points and find the slope of that, that's going to be our change in y over change in x, isn't it? And we can give these ordered pairs here their proper names, right? If we're talking about a function and we're on the function y equal f of x, that's the blue one, then we would be, this ordered pair here would be the point a comma f of a, and this ordered pair here would be b comma f of b. So putting this all together, the average rate of change over this whole interval is just going to be the slope of that line. And we can find the slope of that line, right? We would take the big thing in the y, which is this one, subtract the other y coordinate, right? This is just another way to write the definition of slope here, right? And then we got b minus a. So here we have this is our average rate of change here. So average rate of change. Okay, so specifically here, the line that connects these 2 points, a comma f of a and b comma f of b, this is called a secant line. So if somebody says, find me an equation of the secant line between these 2 points on a graph, we could do that. But let's just do a simple example here. Finding a secant line, it will just amount to finding the slope of your line and then, you know, writing an equation for the line. So let's just do one of these where we can say what the average rate of change is. And let's have some function here, I don't know, 2x squared minus 1 over the interval, let's say 0 to 2. So we want to find the average rate of change of this function here from 0 to 2. So if we were to draw a picture of this, we can definitely draw a picture of this, right? Because we know kind of what that shape looks like, and we can plug in a bunch of x values if we want to. If I put in -1, I'm going to get 1, right? -1 squared is 1 times 2 minus 1 would be 1. If I put in 0, I'm going to get -1. If we put in 1, we're going to get 1 squared. Okay, that's going to be 1. So, you know, plot a bunch more points if you want to, and we can draw a picture here. So here's what our graph looks like. Average rate of change of this nice function between x equals 0 and x equal 2. So graphically, what we're doing here is we are finding the slope of the line connecting this point here where x is 0, that's 0, -1, and the point up here where x is 2. So, you know, we're extending there. So the coordinates of this point are 2, comma, and then whatever we get when we plug that in there, right? And maybe we can do a little scratch work here. Well, we probably don't need to, right? 2 times 2 squared would be 4, times 2 is 8, minus 1 would be 7. So that's relatively quick there. So we can find our average rate of change, right? F of B, so here B is going to be 2. So F of 2 minus F of A here is 0, divided by B minus A, so B minus A. And again, graphically, we're finding the slope of this line right here. And that's, well, right here. So we can say that that's equal to, we know that F of 2 is 7 from our little scratch work. We know that F of 0 is -1 from our, again, little scratch work. And then we got 2 minus 0 is 2. So we've got 7 minus -1 is 8 over 2. So our average rate of change of that function from 0 to 2 is 4.